Okay, today we're going to start our discussion of probability. And chapter 7's probably the longest, it is the longest chapter that we've been in so far this year. It'll take us a little while to get through all the different things we can do with probability. And then near the end, we'll have some more statistics kind of involved as well. So to start this out, we need to talk about what is probability. And so probability is some other words you might think of. Hopefully you think of kind of some of these whenever you think of the word probability. Uncertainty. You might think of that. Likelihood. So it's the likelihood of something occurring. Might think of it as the chance. Oh, can't spell. The chance that something occurs. Possibility. Okay, we think of probability whenever we think about weather events. We think about the probability of, I don't know, a car accident. What's the probability of it raining tomorrow? What's the probability of rolling a certain number on a die? Maybe you're playing Monopoly and you need to roll, 5 in order to land on free parking, so you get all that money. And so you're like, well, what is the probability that I roll a 5 when I roll 2 dice? So these are some of the places where we think about probability in real life. So some of the terminology we're going to be using, I want to make sure that we can use accurately, are listed in the table below. So it says experiment. So the experiment is a process by which you obtain an observation. So we do some type of like repeated events, and we make some observations about them. Typically, our experiments are strategically designed so that we kind of gain the information that we're needing to investigate. So maybe we want to do an experiment about rolling a prime number on 2 dice. And so we might start rolling some dice and recording how often we get a prime, and how many times we roll the dice. And so that would be an experiment to help us explore that probability. A trial is repeating an experiment a certain number of times. Okay, so the more trials you do in an experiment, the more accurate your probability is going to be. So we might do 50 trials to gather some data to tell us the probability of rolling a prime number. So the number of trials completed it kind of tells us how accurate our information might be. If we complete, 2,000 trials of something, that's going to be more accurate than completing 2 trials of something. And so trials are repeating an experiment a certain number of times. So the experiment might be rolling a die, or rolling 2 die. Trials are I rolled my 2 die 1,000 times to gather this information. So the thing that actually happens whenever you do the trial, so you roll your die, which is the experiment. So you roll your dice. The outcome is what could possibly show up. So if you're rolling 2 dice, you could get anything from 1 up to 12. Or no, can't get 1. Sorry, 2 up to 12, right? So you could get the lowest number you get if you roll 2 dice is 2, and the highest number you get is 12. Those are the outcomes for an experiment. Okay. So those are the possible results. So a possible result of an experiment. So you roll 2 die, a possible result, possible outcome would be the number 6. Okay. A possible result or outcome that actually fits our event would be a prime number like 7. That is an outcome that also fits the event. So the event is actually an outcome or a set of outcomes. So an outcome or set of outcomes. All right. So whenever we're talking about rolling 2 dice, what's the probability of getting a prime number? So an event would be, okay, prime numbers. So you don't need to write these, but 2, 3, 5, 7, 11, 13. Oh, we're past 2 dice. Okay, so this is an event. So these 5 outcomes all grouped together form an event. So what is the event is rolling a prime number. Those are the prime numbers. So that would be the event that we have in question. So our sample space is just the set of all possible outcomes of an experiment. So okay, so set of all possible outcomes in an experiment. This would be, if we're rolling 2 dice, this would be all of them. Okay, so that is the sample space for rolling 2 dice. Those are the only outcomes you can get. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. You can't get anything else. We're kind of throwing out those events of, well, what if one of the die lands up against the leg of the table and it's at an angle? Well, we probably re-roll that. That doesn't really count. So that's the sample space for rolling 2 die. I kind of made a note here in your textbook. They use great use of this vocabulary. So if any of this vocabulary is confusing to you, you haven't heard it before, and you want to see like a good paragraph that uses the vocabulary, then I highly recommend going to page 302 in your textbook and reading that paragraph at the top of the page. It's pretty good as far as how they explain those vocabulary words. All right, so we have 2 different types of probability. We've got experimental and theoretical probability. So experimental probability is going to be probability that we generate by repeated experiments, repeated trials. We're curious about the probability of rolling a prime number on 2 dice. So we roll dice 1,000 times. We calculate how many times we get a prime and find our probability that way. Experimental probability is great, and it's actually used a lot in real life. If you think about the likelihood of it raining tomorrow, how about the likelihood of it snowing tomorrow because of the situation we're in now? So the way the weather people, the way they come up with the probability that it's going to snow tomorrow is by looking at past data of similar weather conditions and taking that information and saying, okay, well, tomorrow we have this type of storm coming in from this direction, and we have this humidity, and we have I don't really know exactly what they do, but maybe they have a certain uplift in air or down pressure. I don't know. So they look at all these things and they say, okay, in these conditions in the past, how often did these conditions produce snow? And they say, okay, well, in the past, 30% of the time when we have these conditions, we get snow. And so that's why on the Weather Channel app, it pops up and it says 30% chance of snow tomorrow. It's because in the past, 30% of the time with these weather conditions, we get snow. And so that's just kind of a way they use experimental probability in real life. The experiments or the trials are the previous days that had, previous days that had the same weather conditions. Those are our, the experiment is any day that has similar weather conditions. The trials, however many days that in the past have had the weather conditions that tomorrow is going to have. And that's how they can actually tell us potentially what the weather's going to be like. And I mean, you know how good they are at that, but that is how they come up with experimental probability. So this is calculated based on repeated trials. Or events. Alrighty. Theoretical probability is probably more often used, especially in math. And this is the probability that's obtained by actually kind of doing the math. So theoretical probability is a way that we can quantify probability without having to carry out a large number of trials. So if we're rolling 2 dice and we want to know the probability of rolling a prime, we might look at the number of primes, on the dice, divided by the number of outcomes that we could get. I'm going to erase this in a second. So number of primes divided by the number of outcomes we could get, and that gives us our probability. So one of the big assumptions that gets made whenever we're talking about theoretical probability is we assume that all of the outcomes are equally likely. Well, whenever you roll dice, oftentimes they're not all equally likely. Potentially the dice is weighted one direction. Maybe you don't really shuffle them around in your hands too much, and I don't know, you could throw it in a way that you guaranteed or more likely to get a 6, let's say, or something like that. And so maybe it wouldn't be equally likely. So theoretically though, we often assume that they are equally likely. And so just kind of be aware of that. In theoretical probability, we're oftentimes assuming equally likely events. So for theoretical probability, here's some notation. We have probability of an event A is equal to, and I'll explain what this notation means, n of A over n of U, where n of A is the number of outcomes that make A happen, and n of U is the number of outcomes in the universal set. Okay, or sample space. So universal set is another kind of way to say sample space. So universal set includes everything, sample space includes everything. Okay, so they use U for universal, but that's the number of outcomes in the sample space. So we just take the number of outcomes that fit what we're investigating, and divide it by the number of outcomes that are actually completely possible to come up with our probability. You've done this before, I'm 100% sure. So we'll just practice this a little bit below. So it says, find the probability of each event and decide decide which event is least likely. All die are fair. So all die are fair just indicates that they're not weighted in any direction. So we want to throw a factor of 24 on a 4-sided die. All right, so a 4-sided die is only going to have the outcomes of 1, 2, 3, and 4. A factor of 24, 1 is a factor of 24, 2 is a factor of 24, 24 is divisible by 3, 3 and 8, and 4 and 6. Oh man, so they are all factors of 24. So what is the probability that when you throw a 4-sided die, that it's going to be a factor of 24? So it would be 1. So I'm going to say the probability of A, since this is question A, is equal to 4 out of 4, which is 100% chance. Okay, what's the probability that we throw a prime on an 8-sided die? So an 8-sided die is going to be 1, 2, oh no. Hopefully it looks like it's still recording. I don't know where it went though. Okay, I don't know what happened there. So an 8-sided die is going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's 8 different outcomes. Let's see which ones are prime. So 1 is not prime, 2 is prime, 3 is prime, 5 and 7 are prime. So it looks like 4 are prime. So probability on question B here for event B, there's 4 outcomes that are primes out of a total of 8 outcomes. So half, or 0.5. I'll write as decimal here. Okay, so you could say 50%. The probability is 0.5, or 1 out of 2 are all ways of saying that. All right, what's the probability on this one? Throw at least 11 on a 12-sided die. Okay, so 12-sided die, at least 11. So everything 1 through 10 is less than 11. Let's see. So we're going to throw at least 11. So 11 would count and 12 would count, but nothing 1 through 10 would count. So we need at least 11. So 11 or more. So that's only 11 or 12. So there's 2 outcomes that are at least 11, and they're out of a total of 12 outcomes. So that's 1 out of 6. Or we could write that as a decimal, 0.16. Let's go 3 sig figs, 7. what's the probability we throw at most 3 on a 6-sided die? So 6-sided die, 1, 2, 3, 4, 5, and 6. We want to throw at most a 3. So 3 is the most we want to throw. So we want it to be less than that. So at most a 3 means less than 3. So the probability on D is 3 out of 6, or a half, or 0.5. Alrighty, on the last one, we want to throw a multiple of 5 on a 20-side die. Oh, that's a lot to list. Oops. All right, you might just kind of know that there's going to be 4 of these. So 5, 10, 15, and 20 are multiples of 5. So there's 4 of those. So the probability of this event is equal to 4 out of 20. This is not very likely, which is 1 out of 5, which is 0.2. All right, so which event is the least likely to occur? The most likely to occur is going to be A. The least likely to occur is going to have the lowest probability, which would be C, closely followed by E. Okay, so out of these, our lowest probability is C. Okay, that's the least likely to occur. All right, next one. It says, on a fair coin is flipped 14 times. Predict the number of times you expect a head to be face up. So we have a fair coin. It's flipped 14 times. How many times do we expect a head to show up? Well, a head has a 50% chance of showing up. So a head, whoops. The probability of heads is 0.5, okay, half the time it's going to show up. So in order to predict out of 14, all we have to do is take 14 times 0.5 and get 7. So it doesn't mean that we will for sure have 7 times where we have a head face up. We're just saying that the most likely thing to happen would be that there would be 7 heads and 7 tails. It definitely does not guarantee 7 heads. We could very well flip it 14 times and get 14 tails, no heads. But this is the expected number, would be 7 times. All right, so this next question is kind of an application of what we just did on question 2. So question 3 says, statistical data built up over 5 years shows that the probability of a student being absent at a school is 0.05. There are 531 students in the school. Predict the number of students you expect to be absent on any given day. So if the probability that a student is absent equals 0.05, all we have to do is take that probability times our 531 students, and that gives us 26.55. So we're going to call that 27. So we would expect there to be 27 students absent on any given day. So some things to consider. That would be assuming that every day we have this equal probability of students being absent. So if there's a 0.05 chance of a student being absent, we expect there to be 27 kids absent. However, if this data was collected across the whole school year, typically the best attendance happens in the fall. So we have, in most schools, at least in Ozark, the best attendance happens typically in the first and second quarter. Third quarter typically has the lowest attendance, so that would be during January and February. And March, I think oftentimes because people are getting sick kind of that time of year, we've got higher flu cases, strep throat, that type of stuff. And then fourth quarter is better than third quarter, but still kind of a weak time of the year. So as we kind of roll into summer and vacations and things like that. So this 0.05, might be accurate on like a standard day in March. I don't know. But it could, if it was collected across the whole school year, we'd have to kind of account for the fact that at different times of the school year, there's probably a different probability for that number. So. But we would expect maybe 27 people to be absent if there is a 0.05 chance of a student being absent on any given day. All right. Here's a two-way table. We haven't looked at these yet in this class, but we will, and we're going to keep looking at more of these. And it's important that we can read and understand this. So it says a coastal town carries out a survey of tourists in July of 2018. The accommodation type chosen and the age of the tourist are recorded. The information is given in the table below. All right, so they give us the age and the accommodation type. Okay, so it tells us how old the tourists are and where they stay whenever they're visiting this town. And so we can interpret each of these numbers. So there were 81 people who were between the ages of 18 and 30 who stayed in a camper van during July of 2018. We've got, right, here's this 5170. There were 87 people between the age of 51 and 70 who stayed in a hotel. Typically at the end of these tables, we're going to have an accumulated total. So I'm going to go ahead and add that. So oftentimes you're going to have totals. They might not be given, but you'll very often need to find those. And so we're going to total in this box right here. We can total up the number of people who were 18 to 30 and write that number over there. So I'm going to just add across that column. So 67, 81, and 125, and 32 gives us 305. Okay, then we can go move down to the next box. Let's total up everybody 31 to 50. So 529, this seems like a pretty popular town. So we got 87 plus 76 plus 34 plus 89. So we've got 286 people who are 51 to 70. Okay, greater than 70. Hopefully these numbers are right. I don't have anybody to check me. Okay, and then we can add down as well. So if I add the 67, the 107, the 87, and the 109 together, I get 370. That represents that there are 370 people who stayed in a hotel. Adding down the next column, there were 419 people who stayed in a camper van. There were 247 people who stayed in a tent. I think tent camping is miserable. I don't know how they do it. 32 plus 119 plus 89 plus 54 is 294. 294 people stayed in an apartment. If we add either horizontally this way or vertically this way, we should come up with the same number, which will be the total number of people. Oops. 1,330 people. Okay, they accounted for total. I'm going to go ahead and add down as well just to make sure that I calculated that right. Yep, I got the same number both directions, so it's probably right. All right, now let's see what kind of questions we can answer from this table. So it says a tourist is chosen at random from the survey to receive a promotional offer. Determine what age group the tourist is most likely to belong to. All right, so what age group are they most likely to belong to? If we look over at our totals here, we're looking at the most popular age group. And so there were the largest age group accounted for was 31 to 50. Doesn't mean that, they're guaranteed to be there, but that is the most likely age group that it's to happen in. Find the probability that the tourist chosen belongs to this age group, expressing your answer as a decimal. All right, well, there were 529. Let's do some good notation. So what's the probability that someone's 31 to 50? That's a tourist from 31 to 50. So there are 529 people who fit that age category out of a total of 1,330 people that were surveyed. So if we divide those two numbers, we get a probability of 0.3977, so 8. 1,600 tourists are predicted to visit the town. If the town's hotels have a capacity for 5,000, predict if the town has enough hotel capacity to meet the demand. So from our table, we notice that not everybody stays in a hotel. So originally you would think, holy moly, 1,600 tourists and we only have spots for 5,000. We're going to run out of room. But that's just in the hotels. So let's see, okay, what percent of tourists actually stay in hotels? And then we can see how many of the 1,600 we expect to stay in a hotel. So what is the probability that a tourist stays in a hotel? Well, our hotel number is 370 of these people stayed in a hotel. So if we divide 370 by the total number of people, I'm going to keep a couple decimals because I'm going to use this number. That's everything my calculator showed. So that's the probability that a tourist stays in a hotel. We have 1,600 tourists coming, so we're going to take that number times the 16,000. Oh, let's see, 370. Remember to keep numbers in your calculator whenever possible. So I just press times 16,000. And we've got 4,451 people that want to will likely stay in a hotel, and we've got 5,000 hotels, so I think we're doing all right. Okay, looks like we have the capacity. The next one says 16,000 tourists are predicted to visit the town. Determine the probability that a randomly selected tourist is not staying in the hotel. All right, so if we want to predict a tourist is not staying in a hotel, we need to look at all the totals of the other options. So camper van, tent, and apartment. Alternatively, we know the probability of them staying in a hotel, and these people can either stay in a hotel or choose to not stay in a hotel. So you can take, we got all these people. There's the people, right? We can classify them instead of the 4 categories of hotel, camper van, tent, and apartment. We could classify them as hotel people and not hotel people. And altogether, that should give us our total sample space, our total number of people. So I'm going to calculate this 2 ways. So the first way, I'm going to take the numbers from our table. Camper van, there were 419, 247 that stayed in a tent, and 294 that stayed in an apartment. When I add those together, that gives me a total of 960 people. There were 960 out of a total of 1,330. 0.7218. Okay. Alternatively, since we can divide this sample space into people who are in a hotel and people who aren't, then this probability, the probability they stay in a hotel and the probability that they don't stay in a hotel, should add up to 1. So if I do 1 minus that number from the last question, I will get this number right here. Okay, so that's just another way to think about that probability. All right, thank you for watching. If you have any questions at all, please reach out to me and we'll kind of chat about it over that Google Meet. I hope you guys are doing all right today and staying warm. Thanks for watching.